All right, class, we have officially arrived at the last topic associated with matrices that we will discover in this class, which is the Gauss-Jordan elimination, also known as the reduced row echelon form. So by continuing to apply elementary row operations to the row echelon form in an augmented matrix, you can write the matrix in reduced row echelon form. Notice what that looks like. Notice that if I kind of did a dot, what do we have here? What does this look like? I hope you're looking at them like, whoa, that looks like the identity matrix, because that's exactly what it is. This is useful because substitution will not be needed. Once a matrix is in reduced row echelon form, we know that x equals A, y equals B, and z equals C. Remember, because this is our x column, our y column, our z column, and notice how we have that one-to-one correspondence there. Okay, so transforming an augmented matrix to reduced row echelon form is called the Gauss-Jordan elimination. This is named after Carl Friedrich Gauss and William Jordan. So we're going to solve each one of these and do it in, turn it into Gauss-Jordan elimination. So we're going to start off by writing this with an augmented matrix. So if we turn this into an augmented matrix, we're going to have 1, 2, and negative 1. 1, negative 1, negative 5, negative 1, 1, negative 3, and then write in those answers here, those constants, negative 6, negative 3, and negative 14. This becomes our augmented matrix. Now we need to decide, remember, our goal is to transform this entire side over here into the identity matrix. We want to, so let's write goal to turn this entire side into the identity matrix, okay? So let's go ahead and start thinking about how we can do that. Notice that I'm going to want to make sure to turn this 2 into a 0. So let's start there. Let's go ahead and take row 2 and subtract row 1, okay? But I'm not going to just subtract row 1. I need to subtract negative 2 times row 1. So I'm going to take row 2. I'm going to subtract 2 times row 1, and I'm going to transform that into the new row 2. So let's write out that new matrix here. When I do that, notice that my row 1 stays the same. My row 2 now, I'm going to take row 2 minus 2 times row 1. So 2 minus 2 times 1, that gives me a 0. 2, so negative 1 minus 2 times 1, that's going to give me a negative 3. And then we're going to have 1 minus, it's going to be 1 minus 2 times negative 1, which becomes a positive 2. So that gives us a positive 3 here. Now, our last one is going to be negative 3 minus 2 times negative 6. So it's going to be a positive. So we're going to get 12, end up subtracting 3. So we end up with a positive 9. My last row is going to stay the same, negative 1, negative 5, negative 3, and negative 14. Okay. So now I need to think here. All right, so I got that 0 there that I wanted. Okay, I need to make sure I turn this into a 1, right? So why don't we go ahead and divide everything by 3. So the way that we're going to do that is we're going to divide, and actually we're going to divide by negative 3, or we're going to multiply by negative 1/3 in row 2, and that's going to take and transform row 2 again. So row 1 stays absolutely the same. So 1, 1, negative 1, negative 6. So then we're going to get 0, 1, right? Now, negative 1/3 times 3, that's going to give me a negative 1. Negative 1/3 times 9, that is going to give me a negative 3. All right, and then that last row stays the same. So negative 1, negative 5, negative 3, and negative 14. All right, so now we got to think here. I got that 0 and I got that 1, which is definitely what I wanted, right? But now we need to think of how do we convert this into a 0. So now let's start looking at row 3. So the nice thing about row 3 in this case is that 1 is already positive 1 and 3 is already a negative 1. So let's just combine those two rows. So we would end up with row 3 plus row 1, and we're going to make that change to row 3. So that first row is going to stay the same. That last row, though, now is going to be -1 plus 1, which is 0, -5 plus 1, which is -4, -3 plus -1, which is another -4, and -14 plus -6, that's going to give us a -20. Okay. All right. So now we're looking here, and notice I want to make sure that I turn that -4 into a 0. That's my goal. So I have a 1 here, which is really nice because now I just have to take that row 2, multiply it by 4. So we're going to do R3, row 3, plus 4 times row 2. And again, we're applying that change to row 3. So now here goes our matrix. That first row stays the same. That second row is going to be 0, 1, -1, -3. It stays the same. And now we're doing row 3, just 0, plus 4 times row 2. So -4 plus 4 times 1, that's going to be a 0. Now -4 plus -1 plus 4, that's going to give us a -8. And lastly, -20 plus 4 times -3, that's going to give us a -32. Okay. Now we're getting really close because notice how we have those 3 zeros in that corner we want. Now we're going to take that -8 and we're going to get rid of it because remember we want a 1 there. So let's go ahead and take -1/8 of row 3 and we're going to apply that change to row 3. So row 1 is going to stay the same, 1, 1, -1, -6, 0, 1, -1, -3, 0, 0, 1, and then -1/8 of -32, that's going to be 4. All right, we are looking like we're in good shape. So now notice that this right here, this is row echelon form. Okay, but we don't want row echelon form. We're looking for row reduced echelon form, which means that we are now really interested in getting these values here to turn into zeros. So we have that lower triangular zeros, which is good, but we need to continue here. So in our continuity, notice that now that that last row is all zeros and 1, we can use that to our advantage. So we're going to go ahead and take row 3, add it to row 2, and we are going to use that to change row 2. So we're going to come and do row 3 plus row 2, and now that change is occurring into row 2. So that top matrix remains the same, which is going to be 1, 1, -1, -6. That last one is going to stay the same, which is 0, 0, 1, and 4. But now we're taking row 3 plus row 2. So now notice that row 3 plus row 2, now 1 plus -1, that's going to go to 0, and 4 plus 3, that's going to go to 1. So we're going to get 0, 1, 0, 1. Okay. All right. So now we're left with, all right, let's figure out what do we do with row 1, because now we have to remove 2 of those. So we can go ahead and take row 3, and let's go ahead and add it to row 1. So we're going to take row 3 plus row 1, and we're applying that change to row, not row 3, we're row 1. So we have 1, 0, 0. So this matrix is going to, this last row is going to stay the same. That second row is going to stay the same. And then that first row, when we combine them, notice that this stays 1. When we add those 2, we are going to get a 0 here. And now when we add 4 and -6, we're going to get a -2 here. All right, so now let's look. The only thing we have left to change is this one right here. And I hope you've guessed that, okay, we're going to use the second row here to combine with that first one. So we're going to do row 1 minus row 2. and that change is going to be applied to row 1. So here we go. So 1 minus 1, that's going to give us a 0. 0 minus 0 is a 0. Negative 2 minus 1, that's going to give us a negative 3. And then the rest of these stay the same. Okay. And now notice I have those upper zeros in a triangle. I have those lower zeros. I really have this identity matrix here, which is what I wanted, right? And now from this space, I can just go ahead and read off that x equals negative 3, y equals 1, and z equals 4. So my value is going to be negative 3, 1, and 4. And that's it. That's the answer. That's how we got that answer. All right. I know that was a lot. I want you to take a moment and see if you can do that with example number 2. Again, where you can transform it into row echelon form first, and then continue that work to get row reduced form. All right. So here we have the solution. Is this what you got? Let me walk through it real quickly. So what I ended up doing is I started with the augmented matrix here. But once we had the augmented matrix, I decided to first transition that first row into a leading coefficient of 1. So what I did through my entire solution is I highlighted where my focus was. So for my augmented matrix, I focused on that leading coefficient 1. I wanted to make sure I turned that into a 1, and I did that by multiplying by 1/2. Took that entire row, multiplied by 1/2, and I kept that change in row 1. Then I went from there to focusing on the leading coefficient in row 2. I want to turn that into a 0. And so I did that by adding row 2 plus row 3 and keeping that change in row 2. Lastly, I wanted to go ahead and notice that I made that a negative 1. I want to go ahead and keep that a positive. So all I did was change that sign there. And so I multiplied that row 2 by a negative and got the following in row 2. So that same thing, stayed in row 2. Then I wanted to focus on that negative 1. I want to transform that negative 1 into a 0. So I took row 3 and I added row 1. And I came with this new, and that change was adapted into row 3. Next, I wanted to focus on that 3 and transition it into another 0, trying to get to that lower triangular zeros there. And so I did that by subtracting 3 times row 2 from row 3, keeping the change in row 3. Okay. So as I went on, I kept thinking, all right, how do I get rid of the next value? How do I make sure those leading coefficients are 1 going forward? And that's how I went about to solve which column and what elementary row operation I would do to each one. All right, so that's example number 2. Okay, let's move on. I'm going to have you try example 3. So take a moment to try that one. All right, so for this one, did you obtain the solution -9, 2, and -4? Hopefully you did. You might be wondering, how come, perfect, what happened? Why didn't you write out the row operations? Well, what I wanted to do here is I wanted to start and show you how to use the technology to solve this for us. Because as you can imagine, as matrices get larger and larger and larger, it is not going to be feasible for us to do this by hand. So as always, I teach you how to do it by hand. Now let's move on and use the Desmos matrix calculator to solve this using technology. So we're going to come over here to the calculator. Go ahead and clear all. So what we're going to do is we're going to define a new matrix, but this particular matrix is not going to be, it's going to be our augmented matrix. So if we kind of look back over here, we're plugging in this matrix here. So notice that we have 3 rows and we have 4 columns. So we're no longer looking at a square matrix. So it's going to be 3 rows and 4 columns. So let's go ahead and plug in those values. So we had 3, -12, -6, -27, -1, -1, 2, -1, 1, -5, -1, and -15. So that's our new matrix that we have defined. So what I want you to notice is down here, notice how it says RREF. So this stands for row reduced echelon form. That's what RREF stands for, and that's exactly what we want. So we're going to do row reduced echelon form, and then we're going to go ahead and tie in our matrix A. We're going to go ahead and close this off and enter, and there's our solution. Notice it's already combined and created that identity matrix for us on the left-hand side, and then we got -9, 2, and -4. So, and that leads to our solution here. Okay, so remember, that's what we want to do. We want to be able to first, on Desmos, we are going to define our matrix. And we are inputting the augmented matrix, so we are doing the augmented matrix. And so we can set that equal to A, and then we're going to select RREF of our matrix A. And recall that RREF stands for row reduced echelon. Oh, there's no S. Echelon form. Okay, and so that results in our identity matrix and our solution to our identity matrix, which is going to be -9, 2, and -4. So it's definitely a lot easier to put it into the calculator than it would have been for us to have done that manually. All right, so from our previous lessons, you know that not all linear systems have a unique solution. So linear systems can also have no solution, and they can have an infinite number of solutions. So the row echelon form of a linear system can reveal whether it has one solution, no solution, or an infinite number of solutions. So how do we determine that? Well, we saw the case of one solution when we got all ones down the diagonal, and then we got our answer. So this particular case, right, has one solution, okay? Now, no solution is going to come down here, and notice this last one. This is equivalent to saying that 0z is equal to 5, which then implies that 0 equals 5. But that's not true. That's a false statement. So this would be a false statement. So now infinitely many solutions come into play all the way down here. So notice this. This would imply that 0z is equal to 0, which means that 0 is equal to 0, which is a true statement. So this means that it doesn't matter what we plug in for z, we would end up with the answer right back and it would work. So that's why it leads to infinitely many solutions. Okay, let's look at a couple of here. So let's use our calculator to determine whether the system has one solution, no solution, or an infinite number of solutions. All right, so for this first one, we'll do it together, and then I'll pause and I'll have you kind of try out the other ones on your own. All right, let's go ahead and put this first one into our Desmos calculator. Let's go ahead and clear all. We're going to define our matrix, and it's going to be a 3 by 4. Whoops, 3 by 4. And so we are going to have -7, -8, 7, 31, our augmented matrix here. -4, 8, 4, and 40. And so we're going to go ahead and hit ready. So now I'm going to do RREF, pick my matrix A, close it off, hit enter. So now look at this denominator. I'm going to get 0, 0, 0, 1. So that 0, 1, that's a false statement. 0 can't equal 1. So therefore we're left that this particular system has no solution. Try number 6. Did you get a unique solution for number 6? You should have gotten -2, -8, -3. Hopefully it's what you got. Try number 7. Did you get infinite solution for number 7? Right? So number 7 will look like 1, 0, 0, 3, 0, 0, negative 1, 2, and then I had a whole row down here of zeros, that implying we have infinite solutions. All right, try number 8. All right, for number 8, I got one solution, and the solution was negative 7, 4, 1, so we do have a unique solution for that one. All right, we have 4 more. Let's try number 9. So I got, yes, there's a solution, and I got the point 2, 6, negative 5. Is that what you got? All right, let's look at number 10. I obtained infinite solution for that one. Again, that bottom row being all filled with zeros, which is a true statement. So infinite solutions for number 10. Take a moment to try number 11. All right, for number 11, I got a contradiction down here. 0 cannot equal 1. So therefore, we're left with no solution for this system. Last but not least, let's try number 12. All right, for number 12, I got, yes, there is a unique solution, and the point is negative 1, negative 2, 0. All right, that's it. This concludes our entire section on matrices and linear systems. That's it. We're done with this.